The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, hi. So I've got homework 9 for you, ready to return at the end. The department asked me to do evaluations, but that's the end of the lecture. Then, so everybody knows there's a quiz tomorrow night. And shall I just remember the 4 questions on the quiz? I mean, not the details, but the general idea of the question. Details okay too, yes. Yeah, so there'll be 1 question on a Fourier series. And you should know the energy equality with for all of these possibilities, connecting the function squared with the coefficient squared. A second one on a discrete Fourier transform, cyclic stuff. The third one on the Fourier integral. And have a look at the applications to solving an ODE. I did one in class, the one in class was the one in the book, minus u double prime plus a squared u equal f of x. So this will be, so have a look at that application. This is, of course, on minus infinity to infinity. And then a 4th question on convolution. Okay. And this afternoon, of course, I'll be here to answer any questions from the homework, from any source for these topics. Are there any questions just now, though? I'm okay to take questions. I thought I'd discuss today a topic that involves both Fourier series and Fourier integrals. It's a kind of cool connection, and it's linked to the name of Claude Shannon, who created information theory, who was a Bell Labs guy and then an MIT professor. So I should put his name in, Shannon. Okay. So this is. Yeah, you'll see. So it's not on the quiz, but it gives me a chance to say something important and at the same time review Fourier series and Fourier integrals. So let me start with the problem. The problem comes for an A to D converter. So what does that mean? That means this A is analog. That means we have a function, A for analog, and D for digital. So we have a function, so f of x, say all the way minus infinity to infinity. So we'll be doing, that's where the Fourier integral is going to come up. So that's analog, all x. It's some curve. And people build, and you can buy, and they're sold in large quantities, and something that just samples that function, say at the integers. So now I'll sample that function, and let me take the period of the sample to be 1, so that I'm going to take the values f of n. So now I've got something digital that I can work with, that I can compute with. And so the sampling theorem, well, I mean, the question, yeah, so the sampling theorem is about this question. And it seems a crazy question. When do these numbers, that's just a sequence of numbers, this x was all the way from minus infinity to infinity. And similarly, n is numbers all the way from minus infinity to infinity, but just samples, when does that tell me the function? When can I learn from those samples? When do I have total information about the function? Now you'll say impossible, right? So suppose I draw a function f of x. Okay, and I'm going to sample it at these points. So I'm going to all the way. So these are the numbers. These are my f of n. Sampling at equal intervals, because if we want to use Fourier ideas, equal spacing is the right thing to have. So when could I recover the function in between? Well, you'd say never, because how do I know what that function could be doing in between? So let me take the case when all the samples are 0. And let's think about that case. Suppose, what could the function be if all the samples, if these are all zeros? Forever. Okay. Well, there's one leading candidate for the function, the zero function. Now, if you'll see the whole point of the sampling theorem, if you think about what other functions? Familiar functions. Yeah, I mean, we could obviously all sorts of things. But since we're doing Fourier, we like to pick on the sines, cosines, the special functions, and think about those in particular. So somebody said sines. Now, what function, what sine? So a sine function. Certainly the sine function hits 0 infinitely often. What frequency, so what sine of what, it would give me the same answer, the same samples? If I put this sine function that you're going to tell me, so you're going to tell me it's the sine of something, will have these 0 values at all the integers, at 0, 1, 2, minus 1, minus 2, and so on. So what would do the job? Sine of what will hit 0. So I'm looking for sine functions. I guess I'm looking first for the function that just does that. And what is it? Sine pi x. And now tell me some more. Tell me another function, which will also, it won't be that graph, sine 2 pi x. And all the rest. Okay. Let me just use a word that's kind of a handy word. Of course, let's put 0 on the list here. Okay. So this is this is where k, the frequency, usually appears. This is where 2 pi usually. This is where k. The word I want to introduce is alias. This frequency, pi, is an alias for this had frequency 0. It's a different function, but yet the samples are the same. So if you're only looking at the samples, you're getting the same answer, but somehow the function has a different name. So that frequency and this frequency and all those others would be alias. Can I just write that word down? Because you see it often. Alias. Those are that means two frequencies, like pi and 2 pi and 0 or whatever, that give you the same samples. Okay, so now comes Shannon's question. So we have to make some assumption on the function to knock out those possibilities. We wanted now a limited class of functions for which don't include these guys. So that within this limited class of functions, this is the only candidate, and we have this possibility of doing the impossible, of determining that if I know zeros here, the function has to be 0 everywhere. Okay, now the question is, what class of functions? We want to eliminate these guys, and sort of your instinct is you want to eliminate functions that, if it's not 0, then it's got to get up and back down in everything. It could do different things in different intervals, but somehow it's got to have some of these frequencies, pi or higher, would have to be in there. So this is the instinct, that if I limit the frequency band, so I'm going to say f of x is band limited. Can I introduce that word? I'll maybe take a moment just to ask you if you've seen that word before. How many have seen this word, band limited? Quite a few, but not half. Okay. Band limited means the band is a band of frequencies. So it's the function's band limited when it's transformed. This tells me how much of each frequency there is. If this is 0 in some band, in some band, let's say, all frequencies below something. Let's not even put equal in there. Okay. But at least that's not critical. So band limited, I have to tell you the size of the band. And the size of the band, the limiting frequency is this famous Nyquist frequency. So Nyquist is a guy's name. And the Nyquist frequency in our problem here is pi. This is the Nyquist frequency. If we let that frequency, that's the borderline frequency. And there would be a similar Nyquist sampling rate. Yeah, so Nyquist is the guy who studied the sort of borderline case. And so the point is that if our, say, band limited by pi, I have to tell you, so band limited means that there's some limit on the band. And our interest is when that limit is the Nyquist frequency, the one we don't want to allow. So this is the point. So this will be the idea, that if we take this class of functions, that band limited, those are called band limited functions, and they're band limited specifically by the Nyquist limit. If we take those, then the idea is that the only one, then we can reconstruct from the samples, because the only function that has 0 samples in that class is the 0 function. You see, that class has knocked out as not allowing these guys. Of course, I haven't proved anything yet, and I haven't shown how to reconstruct. Well, of course, we quickly reconstructed the 0 function out of those zeros, but now let me take another obviously important possible sample. Suppose I get 0 samples except at that point where it's 1. Okay, now the question is, what function f of x can I fill in between 0, 0, 0, 0, 1, 0, 0, 0? Can I fill in exactly one function and that comes from this class so that I have now the answer for this highly important sample, the sample that's all zeros except for one, the delta sample, you could say. Okay, so I'm looking for the function now which is 1 at that point and 0 at the others. So here's a key function, and I'll show you what it is. So the function, this function that I am going to mention will get down here, it'll oscillate, it'll go forever. It's not like a spline. Splines made it to 0 and stayed there, right? the cubic spline, for example. Okay, but I guess, yeah, somehow that function, we're not in that league. We're in this band-limited league. In a way, you could say that, I mean, what's the key connection between drop-off of the Fourier transform? So if the Fourier transform drops off fast, what does that tell me about the function? It's smooth, thanks. That's exactly the right word. If the Fourier transform drops off fast, the function is smooth. Okay, this is really an extreme case. It's dropped off totally. You know, it's not just decay rate, it's just zonked out beyond this band of frequencies. And so that gives, you could say, sort of a hyper-smooth function. I mean, so smooth that you know everything by knowing these samples. Okay, now I'm ready to write down the key function, a famous function that has those samples. And that function is sine pi x over pi x. I don't know if you ever thought about this function. And it has a name. Do you know its name? Sinc. It's the sinc function, which is a little, you know, the name's a little unfortunate, mainly because, you know, you're using those same letters, S-I-N, but it's a C that gives it, that means this. So this is called the sinc function, sinc of x. But the main thing is its formula. Okay, well, everybody sees that at x equal 1, the sine of pi is 0. At x equal 2, the sine of pi is 0. All these ones we've seen already. And now what happens at x equals 0? Do you recognize that this function, as x goes to 0, is perfectly good function? I mean, it becomes 0 over 0 at x equals 0, but the limit we know to be 1, right? The sine of theta over theta is 1 as theta approaches 0, right? So that it does have that correct sample. And now what's I claim that that is a band-limited function, and you'll see that that function pushes the limit. It's right, you know, Nyquist barely lets it in. So now here's a calculation. So this is our practice. What is f hat of k for that function? Now let me think how to do this one. So I want to compute the just to understand this better. I want to see that that is a band-limited function and what is its Fourier transform. Okay, now once again, here we have a function where if I want to do, I have to, how best to do this? You could say, well, just do it. As I would say on the quiz, you know, just go ahead and do it. But you'll see, I'm going to have a problem, I think. So but this gives us a chance to remember the formula. So what's the formula for the Fourier integral transform of this particular? So my function is the sinc function, sine pi x over sine pi x. So how do I get it? I do a what here? E to the minus I kx, and am I doing dx or dk? Dx, right? And I'm going from minus infinity to infinity. And do I have a 2 pi? Yes or no? I don't, who knows anyway? Right. In the book I didn't? No. Okay. Good. Okay. Now, well, I don't know the answer here. But so it's much better to start with the answer, right? And check that it. So let me say what I think the answer is. I think the answer is it's a function that's exactly it as I say, it pushes the limit from this is k, It's the square wave. It's 0. The height is 1. It's the function that's 0 all the way here, all the way there. I think that that's the Fourier transform of that function. And just before we check it, see how Nyquist got really pushed up to the wall here, right? Because the frequency is non-zero right all the way to pi. But pi is just 1 point there. And anyway, I think we won't get into a philosophical discussion about whether, is that limited to pi? I don't know whether to put, you saw me chicken out here. I didn't know whether to put less or equal or not. I still don't. This is making the point that that's the key frequency. So this particular function, what I'm saying is this particular function has all the frequencies in equal amounts over a band and nothing outside that band. And that's the Nyquist band. Okay, now why is this the correct answer here? I guess the smart way would be this is a good function, easy function. So let's take take the transform in the other direction. Start from here and get to here, right? That would be convincing because we do know that pair of formulas for f connected to f hat connected to f, they go together. So if I can show that I go from here, that Fourier integral takes me from here to there, then this guy will take me back. So let me just do that, because that's a very, very important one that you should be prepared for, right? So now what do I want to do? Here's my function of k, and so I put this is my function of k. Now I'm hoping that whoops. Now what do I do when I want to do the transform in the opposite direction? It'll be an e to the plus ikx, right? D what? dk now, from k equal minus infinity to infinity. And now I think I do put in the 2 pi. Is that right? Now, and the question is, does that bring back the sinc function? If it does, then this was okay in the other direction, right? If the transform is correct in one direction, then the inverse transform will be correct. So I just plan to do this integral. Now what's the f hat of k? Of course, it's an easy integral now. F hat of k is 1 over between minus pi and pi. So I only have to do over that range where f hat of k is just a 1. And now that's an integral we can certainly do. So I have 1 over 2 pi. Integrating e to the ikx will give me e to the ikx over ix. Now remember, I'm integrating dk. Oh, look, see, we're showing this x now in the denominator that we're hoping for. And now I have to do that between k is minus pi and pi. So this is so I get 1 over 2 pi e to the I pi x minus e to the minus I pi x, right? Over the ix. Okay so far? I was doing a k integral and I get an x answer. And I want to be sure that this x answer is the x answer I want. It's the sinc function. Okay, it is, right? I recognize the sign, e to the I theta minus e to the minus I theta divided by 2, I guess, is the sign. This, right? So I have 1 over 2 pi, and here's the ix. Well, no, the I is part of that sign trick. So I'm just using the fact that e to the I theta minus e to the minus I theta this is cosine plus I sine. subtract cosine, but subtract minus I sine, so that will be 2I sine theta, right? That's, we all know. And now theta is pi x here. So I have 2, let me keep the I there, and 2I sine pi x. You see it works. Just using this, replacing this by the sine, the 2 cancels the 2, the I cancels the I, and I have sine pi x over pi x, that the sinc function. Okay, so that's the function. We've now checked, so we've checked 2 things about this function. It has the right samples, 0, 0, 0, 0, 1 at x equals 0, and then back to zeros. It is band limited, so it's the guy. If this was my sample, if this was my f of n, 0, 0, 0, 1, 0, 0, 0, then I've got it. It's the right function. Okay, now we can create Shannon's sampling formula. Shannon's sampling formula gives me the f of x for any f of n. Maybe you can spot that. Now, so this is going to use this shift invariance. Oh yeah, tell me what the, let's take one step here. Suppose my f of n's were 0, 0, 0, 0, and a 1 there. So suppose, this is, and for the exam too, this idea of shifting is simple and basic. And it's a great thing to be able to do. So what would be, this wouldn't be the right answer. That function produced the 1 at 0. Tell me what function, copying this idea, will produce all zeros except for a 1 at this point. So I'll put this question over here. Suppose I'm all 0 at that point, but at this point I'm up, and then I go back to zeros. What function is giving me that? You see, it does decay because of the x in the denominator. It goes to 0, but not very fast. Okay, what's that function? I replace x by x minus 1, right. So the function here is sine of pi x minus 1 divided by pi x minus 1. I just changed the x to x minus 1. Now again, at x equals 0, this is sine minus pi, it's safely 0. But at x equal 1, that's now the point where I'm getting 0 over 0. So and the numbers are right to give me the exact answer, 1. Okay, so now we see what to do if the sampling turned out to give us this answer. And now can you tell me the whole formula? Can you tell me the whole formula? So now I'm ready for Shannon's sampling theorem. Is that f of x, that if f of x is band limited, then I can tell you what it is at all x. So I'm going back to the beginning of this lecture. It's a miracle that this is possible, that we can write down a formula for f of x at all x only using f of n's. Okay, now it's going to be a sum from n equal minus infinity to infinity, because I'm going to use all the f of n's to produce the f of x. And now what do I put in there? So I want my formula to be correct when I want my formula to be correct in this case, so that if all the f's were 0 except for the middle one, then I want to put sine pi x over pi x in there, the sinc function. I also want to get this one right. If all the f's are 0, so there will only be one term. If this is the term, I want that to show up. Okay, yeah, you can tell me. Suppose this is hitting at n. Yeah, we'll just fix this, and then you'll see it. Suppose that all the others, n minus 1, n plus 1, all those, it's 0. But at x equal n, it's 1. Now, what should I have chosen? What's the correct? I'm just going to make it easy for all of us to guess. What's the good sinc function which peaks at a point n? Again, I'm just shifting it over. So what do I do? Put in, what do I write here? N. I shift the whole thing by n. So that's the right answer when this hits at n. So now maybe you see that this is going to be the right answer for all of them. You see that we're using linearity and shift invariance. The shift invariance is telling us this answer for wherever the 1 hits. That's what we need. And then by linearity, I put together whatever the f is at that point. That would just amplify the sinc. And then I have to put them in for all the other values. That's the Shannon formula. That's the Shannon formula. And this function is band limited. Let's see. What's the, oh, yeah. What's the, do you see that this guy is band limited? We checked, right? We checked that this one, sine pi x over pi x, that was band limited because we actually found the band. Now, just gives us another chance to think aloud. What's the Fourier transform of this guy? My claim is that it's also in this band, non-zero only in the band and 0 outside the Nyquist band. What is the transform of that? What happens if you shift a function? What happens to its transform? So that's one of the key rules that makes Fourier so special, is that if I shift, if I took this sine, let me write this guy again. This was the unshifted one that had this that connected to the, what am I going to call that? The box function, the square wave. Well, box is good. Now, what if I shift that function? If I shift a function, what happens to its Fourier transform? Anybody remember? You multiply it by, so if I shift the function, I just multiply this box function. This is a box function in the K times something e to the I shift, and the shift was 1, right? Is it just e to the ik? D being the shift distance. Oh, the shift distance was n. Right. And possibly minus, who knows? Right. Okay. But what's the point here? The point is that it's still 0 outside the box. Inside the box, instead of being 1, it's this complex guy. But no change. It's still 0 outside the box. It's still band limited. So this is the transform of this guy. And then the transform of this combination would be still in the box, multiplied by some messy expression. So what was I doing there? I was just checking that, sure enough, this guy is band limited. And it's band limited. It gives us the right answer at it gives us the right f of n's, of course. Everybody sees that at x equal n, let's just have a look. Now we've got this great formula. Plug in x equal n. What happens when you plug in x at one of the samples? You look to see what this A to D converter produced at time n. And let's just see. So at x equal n, the left side is f of n. Why is the right side f of that n, that particular n? Maybe I should give a specific letter to that end. So at that particular sample, this left side is f of n, and I hope that the right side gives me f at that capital N, that particular one. Why does it? You're all seeing that at x equal capital N, these guys are all 0, except for one of them, except for the one when little n and capital N are the same, then that becomes the 1, and I'm getting f at capital N. So it'll give me that for the n equal 1, the one term. Yeah. Okay, I don't know if it was necessary to say that. You've got the idea of this sampling formula. Okay. Yeah, I could say more about the sampling, just just to realize that sort of why the technology, people, communication theory is always trying to have a greater bandwidth. You always want a greater bandwidth. But if the bandwidth, which is this, is increased, well, by the way, what does happen? Suppose it's band limited by pi over t. Suppose I can, let's just, I normalize things to choose samples every integer, 1, 0, 1, 2, 3, and that turned out that the Nyquist frequency was pi. Now, what sampling rate would correspond to this band, which could be, well, let me just say what it is. That would be the Nyquist frequency for sampling every t. Instead of a sampling interval of 1, if I sample every t, 2t, 3t, minus t, my sampling rate is t. So if t is small, I'm sampling much more. Suppose t is 1/4. If t is 1/4, then I'm doing 4 samplings. I'm taking 4 samples. I'm paying more for this A to D converter because it's taking 4 samples where previously it took 1. How do I get paid back? What's the reward? The reward is if t is 1/4, then the Nyquist limit is 4 pi. I can get a broader band of signals by sampling them more often. Let me just say that again, because that's the fundamental idea behind it. If I sample more often, so fast sampling would be fast samples would be small t, and then a higher Nyquist, a higher band limited, more functions allowed. If I sample more often, I'm able to catch on to more functions. If I sample, and that's what now communications want, wide bands, and this is where they get limited. This is the you could say the fundamental, I don't know whether to say physical limit, sort of maybe Fourier limit on sampling theory is exactly this Nyquist frequency. Okay, questions or discussion about that? Okay, enough. So that's an example that allowed us to do a lot of things. Okay. Yeah, I did want to ask for your help doing these evaluations. Let me say what I'm going to do this afternoon. I'm going to answer all the questions I can, and I planned, when there is a pause and nobody else asks, I plan to compute the Fourier integral and Fourier series, Fourier series, for a function that has it's going to be like the one today, except this is going to be have a height of 1 over h and width of h. So that's if in case you're not able to be here this afternoon, I thought I'd just say in advance what calculations I thought I would do. So there's a particular function, f of x. It happens to be an even function. We'll compute its Fourier coefficients, and we'll let h go to 0 to see what happens. It's just a good example that you may have seen on older exams. Okay. Well, can I just say a personal word before I pass out? So evaluations, if you're willing to help and just leave them on the table, would be much appreciated. I'll stretch out the homeworks. I just want to say I've enjoyed teaching you guys very much. Thank you all. And yeah, thanks.